settle into the sleepy mind channel. Tonight, we enter one of the strangest places ever discovered by science. A hidden world where stars collapse, where gravity bends reality itself, and where even light can disappear forever. Black holes are often described as cosmic monsters, but the truth is much more fascinating than fearsome. These objects are part of the natural machinery of the universe. They shape galaxies, bend time, move stars across enormous distances, and quietly influence the framework of space itself. For many years they existed only as mathematical ideas, written carefully onto paper by scientists trying to understand gravity. Even today, black holes still feel almost unreal, like something imagined for science fiction, rather than something truly waiting out there among the stars. If you enjoy calm science stories like these, feel free to like and subscribe. More videos are posted weekly, and you can also check out the playlist for various topics and relaxing all-night listening. For most of human history, nobody could have imagined an object so dense that light itself could not escape. Ancient people looked into the night sky and saw patterns, myths, wandering planets, and distant stars. The sky felt permanent and calm. Even early astronomers with telescopes believed the universe was mostly orderly and understandable. Yet hidden inside that calm darkness were objects so extreme that they would eventually challenge nearly every major idea about physics, gravity, energy, time, and space. Black holes would become one of the greatest scientific discoveries ever made, not because they destroy everything around them, but because they reveal how strange the universe truly is when gravity becomes remarkably powerful. A black hole begins with gravity. Gravity is one of the weakest forces people experience in daily life, yet it is also the force that shapes the largest frameworks in existence. A simple refrigerator magnet can overpower the gravity of the entire Earth when lifting a paperclip from a table. Yet gravity possesses one important advantage over every other force in nature. It works across enormous distances and never switches off. Every grain of sand, every drop of water, every planet, moon, star, and galaxy contributes to gravity. Over immense distances and vast amounts of time, gravity slowly becomes the architect of the cosmos. A black hole is a region of space where gravity becomes so strong that escape becomes impossible. The gravity is not magical, and it does not behave like a giant vacuum cleaner, pulling everything inward from across the universe. Instead, matter becomes compressed into a remarkably tiny area. The more mass squeezed into a smaller region, the stronger gravity becomes near that region. Black holes represent the most extreme example of this process ever discovered. Their gravity becomes so intense that the speed needed to escape exceeds the speed of light itself. Since nothing can travel faster than light, nothing that crosses too close can ever leave again. Sunlight crosses space for millions of years before reaching a planet. Light escapes exploding stars, reflects from oceans, travels through glass, and moves across the universe at incredible speed. Human beings naturally assume light can always continue forward, yet black holes reveal there are limits even for light itself. Near a black hole, gravity bends the paths that light normally follows. Space itself becomes curved. Light is not exactly being grabbed and dragged backward. Instead, the very shape of space changes around the black hole so severely that every possible path leads inward. To understand how this happens, it helps to imagine standing on a steep mountainside during heavy rain. Water naturally flows downhill because the shape of the land guides its movement. Now imagine the mountainside becoming steeper and steeper until every drop of water is forced downward, no matter how fast it moves. Around a black hole, space behaves similarly. The curvature becomes so deep that every direction eventually points inward. Even light cannot climb back out once it passes a certain boundary. The story of black holes truly begins with stars. Stars may appear peaceful from Earth, glowing softly in the night sky, but inside every star, an enormous battle takes place every second. Gravity constantly pulls the star inward, trying to compress it tighter and tighter. At the same time, nuclear reactions deep inside the core release tremendous energy, pushing outward. A star survives because these two forces remain balanced against one another. Gravity squeezes inward, while energy pushes outward. The balance can last for millions or even billions of years, depending on the size of the star. Large stars live faster and die younger. They burn through their fuel at astonishing rates. Deep inside their cores, hydrogen atoms combine into helium, releasing energy in the process. Later, heavier elements begin forming. The star becomes layered similar to an onion, with different reactions happening at different depths. Yet this process cannot continue forever. Eventually, the star begins running out of usable fuel. The outward pressure weakens. Gravity, which never stopped pushing inward for even a single moment, suddenly begins to win. The collapse that follows is one of the most violent events in the universe. Imagine a sphere larger than the sun beginning to fall inward under its own weight. Matter rushes toward the center at incredible speed. Temperatures rise dramatically. Pressure becomes almost beyond comprehension. In some cases, the outer layers explode outward in a supernova, while the inner core continues collapsing. If enough mass remains after the explosion, nothing can stop gravity from compressing the core further and further inward. At this stage, the star no longer behaves like ordinary matter. The collapse continues until an entirely new object forms. A black hole is born. The original star may have once stretched across millions of kilometers of space, yet the remaining mass becomes packed into an unbelievably small region. Gravity near this compressed object becomes extreme beyond normal experience. Nearby matter, light, and even time itself begin behaving differently. One remarkable detail about black holes is that they are created through completely natural processes. They are not accidents or mistakes in the universe. Massive stars have been forming and dying for billions of years. Long before Earth existed, ancient stars collapsed into black holes across countless galaxies. Some of those black holes still drift silently through space today. Others sit at the centers of galaxies, influencing billions of stars around them. The universe has likely produced enormous numbers of black holes across cosmic history. For many people, black holes feel frightening because they are associated with destruction and disappearance. Yet black holes are also part of creation. When massive stars explode, they scatter heavy elements across space. Elements like iron, calcium, oxygen, and carbon spread into enormous clouds that later help form planets, oceans, mountains, and living organisms. The iron inside human blood was once forged inside ancient stars, long before the sun existed. In a real sense, the deaths of stars helped make life possible. Black holes also helped scientists unlock deeper understanding about reality itself. They forced physics to confront questions that once seemed impossible. What happens to time near intense gravity? Can space bend? What occurs when matter becomes unimaginably dense? Are there limits to what science can explain? Black holes sit directly at the edge between what humanity understands and what still remains mysterious. They are both scientific objects and cosmic puzzles waiting in darkness. The strange beauty of black holes comes partly from this mixture of certainty and mystery. Scientists understand many details about how gravity behaves around them. Equations can predict orbits, motion, and energy with astonishing accuracy. Yet the deeper one examines black holes, the stranger reality begins to feel. Time slows, space curves, light bends. Familiar ideas stop behaving normally. Black holes reveal that the universe is much more flexible and unusual than daily human experience would ever suggest. Far above Earth tonight, beyond the stars visible to the eye, countless black holes remain hidden across the universe. Some drift quietly through empty regions of space. Others feed on nearby gas glowing brightly enough to outshine entire galaxies. Some are only a few times heavier than the Sun. Others contain billions of times more mass. All of them exist because gravity, given enough matter and enough time, can create objects of astonishing power. The boundary surrounding a black hole is known as the event horizon. This invisible edge marks one of the most important ideas in modern astronomy because it separates two very different regions of reality. Outside the event horizon, escape remains possible. Light can still travel away. Matter can still move outward if enough speed exists. Information can still reach distant observers across space. Yet once anything crosses beyond that boundary, escape becomes impossible. No signal returns, no light emerges, no message travels outward again. The event horizon represents the true point of no return. One reason black holes feel so mysterious is because the event horizon cannot actually be seen directly. There is no solid surface floating in space. There is no wall, cloud, or visible shell surrounding the black hole. If a spacecraft somehow approached one slowly enough, the crew would not suddenly collide with an object the way an aircraft hits a mountain. The event horizon is instead a mathematical boundary created by gravity itself. Crossing it changes what paths through space remain possible. Beyond that point, every future direction leads inward. A shoreline marks where land meets water. A doorway separates one room from another. A cliff edge divides stable ground from empty air. The event horizon behaves differently because it is created by the geometry of space itself. Space around a black hole becomes curved so severely that inward movement becomes unavoidable beyond a certain distance. Even light, which normally travels across the universe freely, can no longer find a path outward once it crosses the horizon. Scientists often compare this process to a river flowing toward a waterfall. Imagine standing beside calm water upstream, where swimming against the current remains easy. Closer to the waterfall, the water moves faster and faster. Eventually, the current becomes so strong that even the fastest swimmer could no longer move backward against it. Beyond a certain point, every movement leads toward the edge. Around a black hole, space behaves similarly. Outside the event horizon, movement away remains possible. Inside the horizon, all paths lead inward toward the center. The event horizon also changes how time appears to pass. According to general relativity, gravity influences time itself. Near powerful gravity, time slows compared to regions farther away. This effect becomes extremely noticeable around black holes. To a distant observer watching from safely far away, an object approaching the event horizon would appear to slow more and more over time. The object would seem to move increasingly slowly as light escaping from it became stretched and weakened. Eventually, the image would fade into darkness. Yet for the person actually falling inward, the experience would feel completely different. Time would seem normal from their own perspective. They would continue moving toward the black hole without noticing any sudden change exactly at the horizon itself. This difference between outside observation and personal experience is one reason black holes became such important scientific puzzles. They reveal that time is not fixed and universal in the way people once imagined. Gravity changes the flow of time itself. Black holes are often described as invisible objects, and in one sense this description is completely accurate. A black hole does not produce visible light from inside the event horizon because light cannot escape from within it. Unlike stars, black holes do not shine through nuclear reactions. Unlike planets, they do not reflect sunlight from solid surfaces. If a black hole existed alone in completely empty space, detecting it would become extremely difficult because nothing visible would mark its position directly. Yet black holes rarely remain entirely hidden. Their gravity influences nearby matter in dramatic ways. Gas clouds, dust, stars, and even light itself respond to the enormous gravity surrounding them. Scientists therefore detect black holes by studying their effects on nearby objects rather than by observing the black hole directly. In many ways, black holes are similar to wind. Wind itself cannot be seen directly, yet moving leaves, drifting clouds, and bending trees reveal its presence clearly. Black holes announce themselves through gravity. One of the earliest clues came from observing stars moving strangely through space. In some regions of the universe, stars appeared to orbit invisible objects possessing enormous mass. The stars moved too quickly for the visible matter nearby to explain their motion. Something massive had to exist there, yet telescopes revealed nothing visible occupying that region. Gravity exposed the hidden object long before direct evidence became available. This process follows the same basic rules people observe daily on Earth. If leaves suddenly swirl across a quiet street, people immediately know moving air must exist, even if the wind itself remains invisible. If ocean tides rise and fall, the gravity of the moon reveals itself through movement of water. Human beings constantly detect invisible forces indirectly through their influence on visible objects. Astronomy works in much the same way. Scientists study motion, energy, and light to uncover objects that cannot be observed directly. Near black holes, gravity becomes so strong that nearby stars may orbit at astonishing speeds. Some stars move around invisible centers faster than entire solar systems travel through galaxies. These rapid motions provide important evidence about the mass hidden inside those regions. By carefully measuring movement, astronomers can estimate the size and mass of the invisible object producing the gravitational pull. Again and again, the calculations point toward black holes. Gravity also bends light itself near black holes. Normally, light travels in straight lines through space, but gravity can curve those paths. Around a black hole, this bending becomes dramatic. Light from distant stars may become stretched, warped, or redirected while passing nearby. In some cases, entire rings of distorted light appear around massive objects because gravity bends the light from objects behind them. This phenomenon helped confirm many predictions about how gravity behaves under extreme conditions. The invisible nature of black holes created doubt among some scientists for many decades. Early researchers wondered whether black holes truly existed or whether the mathematics simply predicted strange, impossible objects. Yet as telescopes improved and observations became more detailed, evidence continued growing stronger. The universe repeatedly revealed regions where invisible mass controlled the motion of surrounding matter, exactly as black hole theory predicted. One especially important discovery involved the center of the Milky Way galaxy. Astronomers observed stars near the galactic center, moving at extraordinary speeds around an apparently invisible object. Year after year, scientists tracked those stellar orbits carefully. The motion revealed that an enormous amount of mass occupied a surprisingly small region. No known cluster of ordinary stars could explain the observations. The evidence strongly pointed toward a supermassive black hole hidden at the center of the galaxy itself. Although black holes themselves remain invisible, the regions surrounding them can become some of the brightest places in the entire universe. This strange contrast surprised scientists for decades. An object famous for trapping light somehow creates environments powerful enough to produce vast amounts of energy and radiation. The explanation comes from matter falling toward the black hole. Long before gas and dust disappear beyond the event horizon, gravity transforms their motion into heat, light, and tremendous energy. Space may appear empty when viewed from Earth, yet vast amounts of matter drift between stars and galaxies. Clouds of gas stretch across vast regions. Dust particles float through darkness. Fragments from exploded stars travel silently through space for millions of years. Near a black hole, this material rarely falls straight inward immediately. Instead, gravity pulls the matter into a rotating disk surrounding the black hole. This spinning framework is called a spinning disk. And spinning disk forms because matter approaching the black hole already possesses motion. Very little in the universe remains perfectly still. Stars rotate through galaxies. Gas clouds drift across space. Dust particles carry momentum from earlier events. When this material approaches a black hole, gravity pulls it inward, while its existing motion causes it to circle around the black hole at enormous speed. The result resembles water spiraling around a drain, though on a scale far beyond normal imagination. Inside the spinning disk, matter becomes crowded together while rotating at incredible velocities. Inner regions of the disk move faster than outer regions because gravity grows stronger closer to the black hole. This difference creates friction throughout the disk. Gas particles collide constantly. Temperatures begin rising dramatically. The once cold matter drifting quietly through space transforms into intensely heated plasma, glowing across enormous distances. The temperatures inside some spinning disks become difficult to comprehend through ordinary experience. Certain regions can reach millions of degrees. Matter there becomes hotter than the surface of many stars. Under such conditions, the disk produces vast amounts of radiation, including visible light, ultraviolet radiation, and powerful X-ray radiation. Ironically, the area around a black hole can therefore become brighter than entire galaxies, even while the black hole itself remains completely dark. This process helps explain why some black holes became easier to detect than scientists first expected. The black hole itself hides behind the event horizon, yet nearby, matter announces its presence dramatically while spiraling inward. Telescopes observing distant galaxies sometimes detect intense glowing regions powered by supermassive black holes feeding on surrounding matter. These active regions release astonishing energy across space. One useful way to picture a spinning disk is to imagine traffic moving toward a busy city center during rush hour. Far away from the center, cars move smoothly with plenty of room between them. Closer inward, vehicles become crowded together. Friction increases. Heat builds from engines and braking. Movement becomes chaotic and compressed. Around a black hole, gas and dust experience a somewhat similar process, except the speeds and temperatures become vastly more extreme. Matter within the spinning disk may orbit the black hole thousands of times before finally crossing the event horizon. During that long spiral inward, vast amounts of energy are released. The energy comes partly from gravity itself. As matter falls deeper into the gravitational well surrounding the black hole, potential energy converts into motion and heat. This conversion process becomes remarkably efficient. In some cases, black holes can release more energy from falling matter than stars release through nuclear reactions. This fact often surprises people because black holes are commonly associated only with destruction and disappearance. Yet black holes also function as cosmic engines capable of transforming matter into extraordinary energy. Some active black holes produce enough radiation to influence entire galaxies around them. The energy flowing outward from the surrounding disk can heat nearby gas clouds, shape star formation, and alter the motion of matter across enormous regions of space. Not every black hole feeds actively all the time. Many remain quiet because little matter exists nearby. A black hole drifting through relatively empty space may produce almost no visible effects. Without surrounding gas or dust, the spinning disk becomes weak or disappears entirely. The black hole remains dark and difficult to detect. Yet when enough material gathers nearby, activity can increase dramatically. The black hole suddenly becomes surrounded by glowing matter spiraling inward at tremendous speed. Some of the brightest objects ever discovered are called quasars. Early astronomers found these strange objects appearing almost star-like through telescopes, yet they released vastly more energy than ordinary stars could produce. Later observations revealed that quasars are powered by supermassive black holes, consuming vast amounts of matter at the centers of distant galaxies. The glowing spinning disks surrounding them outshine billions of stars combined. The energy released around active black holes travels astonishing distances across the universe. Light leaving certain quasars began its journey billions of years ago, before Earth even formed in its present state. Tonight, some of that ancient radiation still crosses space silently toward distant galaxies. Black holes therefore help scientists study not only gravity, but also the deep history of the universe itself. The physics inside spinning disks remains extremely complicated, because many powerful processes happen simultaneously. Gravity pulls matter inward. Friction heats the disk. Magnetic fields twist and move through the plasma. Radiation escapes outward, while fresh material continues falling inward. Scientists use high-level mathematics and computer simulations to study these regions because direct observation remains difficult, even with modern telescopes. One especially fascinating detail involves the speed of matter near the black hole. Material orbiting close to the event horizon may move at a significant fraction of the speed of light. At such enormous velocities, familiar human experience no longer provides useful comparisons. Motion, energy, and time begin behaving according to the strange rules described by relativity. Black holes therefore create natural laboratories where scientists can observe physics under conditions impossible to reproduce on Earth. As matter spirals closer and closer toward a black hole, vast amounts of energy continue building inside the surrounding disk. Gravity does much more than simply pull objects inward. Under the extreme conditions near a black hole, gravity transforms motion into heat, light, radiation, and powerful streams of particles capable of crossing enormous distances through space. Some of the most energetic events ever observed in the universe begin near objects famous for trapping light and hiding themselves in darkness. One of the most important ideas in modern physics is that mass and energy are deeply connected. Matter is not entirely solid and permanent in the way people once believed. Instead, mass can become energy under the right conditions. Stars perform this conversion continuously through nuclear reactions deep inside their cores. Black holes create another powerful version of this process through gravity and motion. As matter falls inward, tremendous amounts of gravitational energy become released into the surrounding environment. A useful way to picture this process is to imagine rolling a heavy stone down a mountainside. At the top of the hill, the stone possesses stored energy because of its position. As it falls, that stored energy converts into motion. If the stone crashes into obstacles along the way, heat and sound are produced as well. Around a black hole, matter falls into an enormously deep gravitational well. The closer inward the material travels, the more energy becomes released. The difference is scale. A falling stone on Earth releases only a small amount of energy compared to the immense energy produced near black holes. Gas spiraling inward may travel at extraordinary speeds while heating to millions of degrees. Friction, compression, and violent motion transform ordinary matter into intensely energetic plasma. Radiation pours outward across space. In some cases, the energy released from falling matter rivals the brightness of entire galaxies filled with billions of stars. Scientists discovered that black holes can convert matter into energy with remarkable efficiency. In certain situations, more energy may emerge from matter falling into a black hole than from nuclear reactions inside stars. This fact seems almost backwards at first, because black holes are usually imagined only as consumers of matter. Yet the process surrounding the black hole becomes extremely energetic before the matter disappears beyond the event horizon. One of the strangest and most beautiful features near active black holes involves the formation of enormous particle jets. These jets emerge from regions close to the black hole and blast outward into space at astonishing speeds. Instead of matter falling inward in every direction quietly, some material becomes accelerated outward along narrow pathways extending far above and below the spinning disk. These jets can travel across distances so enormous that they stretch beyond entire galaxies. The exact process behind jet formation remains an active area of research, but magnetic fields appear to play an important role. The spinning disk surrounding the black hole contains electrically charged particles moving rapidly through extreme conditions. Powerful magnetic fields twist and tighten through the spinning plasma, similar to invisible elastic bands. Near the black hole, these fields can channel energy and particles outward into focused streams, moving at tremendous speed. To imagine this process more clearly, it helps to think about water spraying from the nozzle of a pressure washer. Water enters from many directions, but exits through a narrow opening with concentrated force. Around black holes, matter and energy become organized by magnetic fields into narrow jets capable of crossing unimaginable distances through space. The result is one of the most dramatic sights in the cosmos. Some jets travel at speeds approaching the speed of light itself. Radiation from these jets can be detected across billions of light years. Even though the black hole remains invisible, the jets reveal intense activity taking place nearby. Telescopes observing distant galaxies sometimes detect enormous beams of energy extending outward from galactic centers. At the heart of many of these galaxies sits a supermassive black hole, quietly powering the activity. The scale of these jets can become difficult to comprehend through ordinary human experience. A jet emerging from a supermassive black hole may extend for hundreds of thousands of light years through space. Entire galaxies could fit inside portions of these frameworks. Matter accelerated near a black hole can therefore influence regions vastly larger than the black hole itself. The effects of gravity spread outward across enormous cosmic distances. These jets also interact with surrounding gas clouds and galactic material. As the streams move outward, they heat nearby regions, stir enormous clouds of gas, and influence where new stars may eventually form. In some galaxies, black hole activity appears capable of slowing star formation by heating gas so intensely that it cannot collapse easily into new stars. In other regions, the motion from jets may compress clouds and encourage new stellar formation. Black holes therefore participate in shaping the evolution of galaxies themselves. For many years, people imagined black holes mainly as isolated cosmic traps, pulling everything inward forever. Modern astronomy revealed a much more complicated picture. Black holes interact continuously with their environments. They release energy, influence galactic motion, shape nearby matter, and help organize enormous cosmic regions. In many ways, black holes behave less like simple destroyers and more like engines participating in the larger machinery of the universe. The energy surrounding active black holes can become so powerful that entire galaxies appear changed by their presence. Some galaxies contain bright central regions, known as active galactic nuclei, where supermassive black holes feed on surrounding material. Radiation from these regions may outshine the combined light of billions of stars across the rest of the galaxy. The black hole itself remains hidden, yet its influence dominates the surrounding environment. The idea that invisible objects can shape entire galaxies once seemed difficult to believe. Yet observation after observation continues confirming the enormous influence black holes possess. Their gravity organizes motion near galactic centers. Their energy alters surrounding gas. Their jets stretch across cosmic distances, carrying matter and radiation outward through space. Black holes are not isolated curiosities hidden quietly in darkness. They are active participants in the ongoing evolution of the universe. Not all black holes are the same. Some form from the collapse of individual stars and remain relatively small on cosmic scales. Others grow into enormous objects containing millions or even billions of times the mass of the Sun. Across the universe, black holes exist in different sizes and environments, each shaped by its own history. Although the physics surrounding them follows the same basic laws, the scale can vary tremendously. Some black holes drift quietly through galaxies almost unnoticed, while others dominate the centers of enormous galactic systems. The smallest widely known category is called a stellar black hole. These black holes form when massive stars reach the end of their lives and collapse inward under gravity. Earlier, the star may have appeared bright and stable for millions of years, producing light and heat through nuclear reactions deep inside its core. Yet once the fuel begins running low, gravity slowly gains control. The collapse eventually compresses the remaining core into a remarkably dense object where escape becomes impossible. Most stellar black holes contain several times the mass of the Sun, packed into a surprisingly small region of space. To understand how extreme this compression becomes, imagine squeezing the mass of a star into an area smaller than a city. The density grows so enormous that gravity near the object changes the behavior of light, matter, and time itself. These black holes may seem small compared to supermassive black holes, yet their gravity remains tremendously powerful close to the event horizon. Astronomers believe the universe contains enormous numbers of stellar black holes. Massive stars have been forming and dying throughout cosmic history for billions of years. Every large galaxy likely contains countless black holes created from ancient stellar collapses. Most remain hidden because they produce little visible activity. Some drift silently through empty regions of space. Others orbit companion stars while slowly gathering matter from them. Many probably remain completely undetected. One reason stellar black holes became easier to study involves binary star systems. In some regions of space, a black hole orbits closely with a normal star. The gravity of the black hole slowly pulls gas away from its companion. This stolen matter forms a spinning disk around the black hole and heats dramatically while spiraling inward. The glowing radiation produced by the disk reveals the hidden black hole nearby. Without this surrounding activity, many stellar black holes would remain nearly invisible. Far larger black holes exist at the centers of many galaxies. These are known as supermassive black holes. Unlike stellar black holes formed directly from single collapsing stars, supermassive black holes contain extraordinary amounts of mass gathered over immense periods of time. Some contain millions of times the mass of the Sun. Others reach billions of solar masses. They are among the largest and most influential objects ever discovered. The existence of supermassive black holes puzzled scientists for decades because their size seemed difficult to explain. A single collapsing star could not create something so enormous directly. Astronomers now believe supermassive black holes likely grew gradually over long stretches of cosmic history. They may have formed from smaller early black holes that merged together and consumed surrounding matter over billions of years. Galaxies themselves probably helped feed and grow these hidden giants. One remarkable fact is that many galaxies appear closely connected to the supermassive black holes at their centers. The size of the central black hole often relates to the size of the surrounding galaxy. This connection suggests black holes and galaxies evolved together throughout cosmic history. Rather than being separate objects sharing the same location by coincidence, they may have influenced one another continuously while galaxies formed and changed over billions of years. The Milky Way galaxy also contains a supermassive black hole at its center. Hidden deep within the crowded galactic core lies an object known as Sagittarius, a star. This black hole contains millions of times the mass of the Sun packed into a relatively small region of space. Although invisible directly, its presence reveals itself through the motion of nearby stars orbiting around it at extraordinary speeds. It can feel strange to realize that the galaxy containing Earth revolves partly around an invisible object hidden far away among dense star fields. Human beings often imagine themselves living inside a stable and ordinary cosmic neighborhood. Yet at the center of the Milky Way lies a region where gravity becomes extreme and stars race around a hidden supermassive black hole at remarkable speed. The universe contains frameworks much more unusual than daily life ever suggests. Scientists continue studying black holes of many sizes because each category reveals different pieces of physics and cosmic history. Stellar mass black holes help researchers understand how massive stars die. Supermassive black holes help explain how galaxies grow and evolve. Smaller black holes reveal the behavior of gravity under extreme conditions, while larger ones shape entire cosmic environments across enormous distances. The diversity of black holes also demonstrates how flexible the universe can become through gravity. The same physical force capable of holding planets in orbit around stars can also compress matter into invisible regions, powerful enough to influence entire galaxies. From stellar remnants only a few times heavier than the Sun to giant black holes containing billions of solar masses, gravity shapes frameworks across every scale of the cosmos. Deep within the center of the Milky Way galaxy, hidden behind enormous clouds of gas and dust, lies the supermassive black hole known as Sagittarius A star. Human eyes cannot see it directly from Earth because thick regions of interstellar material block much of the visible light traveling from the galactic core. Yet despite remaining invisible, the black hole quietly shapes the motion of nearby stars through gravity. Entire stellar systems orbit around a hidden object containing millions of times the mass of the Sun. The center of the Milky Way is one of the busiest and most crowded regions in the galaxy. Stars gather there much more densely than in the quieter regions surrounding the solar system. Gas clouds drift through the area, while ancient stars orbit through darkness through powerful gravity. Somewhere inside that crowded environment sits the invisible black hole, controlling the motion of nearby objects, much like the Sun controls the planets of the solar system. For many years, astronomers attempted to understand what existed at the galactic center. Early telescopes could not see clearly through the dense clouds blocking visible light. The region appeared mysterious and difficult to study, yet as technology improved, scientists developed instruments capable of detecting infrared radiation, allowing them to peer deeper through the dust. Slowly, the hidden movement of stars near the galactic center began revealing a remarkable truth. Some stars near Sagittarius A star move at astonishing speeds. Instead of drifting slowly through space, they race around invisible paths under the pull of immense gravity. Certain stars complete long curved orbits around the hidden center, similar to planets circling the Sun, except their motion becomes far faster and more extreme. By carefully tracking these stellar movements over many years, astronomers calculated the mass required to produce such strong gravitational effects. The results were remarkable. Only an object containing millions of solar masses compressed into a relatively small region could explain the observed motion. No cluster of ordinary stars could remain packed so tightly together without becoming unstable. Again and again, the calculations pointed toward the same conclusion. At the center of the Milky Way exists a supermassive black hole, hidden from direct view, yet clearly revealed through gravity. This method of discovery demonstrates one of the most powerful ideas in astronomy. Scientists often study objects not by seeing them directly, but by observing how they influence their surroundings. Human beings use similar reasoning constantly in daily life. People may not see the wind itself, yet bending trees and drifting leaves reveal its presence immediately. In the same way, stars moving rapidly around invisible centers reveal the hidden gravity of black holes. The stars orbiting near Sagittarius, a star, move through space with extraordinary precision. Their paths follow predictable curves shaped by gravity. Some travel on elongated orbits, carrying them close to the black hole before swinging outward again. Others remain farther away, while still responding to the immense mass hidden at the galactic center. These stellar motions provide scientists with valuable opportunities to test theories about gravity under extreme conditions. One especially important observation involved a star called S2. Astronomers tracked its orbit carefully for decades as it traveled around Sagittarius A star. At its closest approach, the star moved at incredible speed while passing near the black hole. The measurements closely matched predictions from general relativity, providing powerful confirmation that gravity behaves exactly as Einstein described, even in extremely strong gravitational environments. The motion of stars around black holes also reveals something larger about galaxies themselves. Galaxies are not random collections of stars drifting aimlessly through space. They are organized systems shaped by gravity across enormous distances. Black holes often sit at their centers, helping influence the framework and motion surrounding them. The relationship between galaxies and their central black holes appears deeply connected. For a long time, scientists thought galaxies might simply contain black holes by coincidence. Modern research suggests something much more important. The growth of galaxies and the growth of supermassive black holes may have happened together throughout cosmic history. As galaxies formed from vast clouds of gas and dark matter, material gathered toward their centers, where black holes gradually grew larger over billions of years. In turn, the black holes influenced the galaxies surrounding them. Energy released near active black holes could heat nearby gas clouds, alter star formation, and affect how matter moved through the galactic core. The relationship became a continuous interaction rather than a simple one-way process. Galaxies helped feed black holes, while black holes shaped galactic environments in return. It is difficult to imagine the true size of these systems because galaxies themselves are enormous beyond ordinary human understanding. The Milky Way alone contains hundreds of billions of stars spread across vast distances. Light traveling at incredible speed still requires about 100,000 years to cross the galaxy from one side to the other. Yet despite this immense scale, gravity from the central black hole still influences the crowded inner regions surrounding it. The solar system exists safely, far from the galactic center, within one of the spiral arms of the Milky Way. Earth does not orbit dangerously close to Sagittarius, a star. In fact, the Sun itself travels around the galactic center, along with countless other stars. The entire solar system slowly moves through the galaxy through its combined gravitational framework. Even the quiet night sky above Earth participates in a larger cosmic motion, unfolding over enormous stretches of time. One full orbit around the center of the Milky Way requires the Sun roughly 230 million years. When dinosaurs walked across Earth, the solar system occupied a different region of the galaxy entirely. Since the formation of Earth, the Sun has completed only a relatively small number of galactic orbits. Human history represents only a tiny fraction of this larger motion happening continuously through space. Black holes therefore exist, not only as fascinating individual objects, but also as part of the architecture of the cosmos. Their gravity helps organize matter across galactic scales. Their energy influences star formation. Their presence shapes the movement of nearby stars through enormous spans of time. Modern astronomy increasingly reveals that black holes participate directly in the framework and evolution of galaxies across the universe. One of the strangest discoveries connected to black holes is that gravity does not only affect matter and motion, gravity also affects time itself. For most of human history, time was imagined as something constant and universal, flowing equally everywhere. A clock on Earth and a clock somewhere far away were assumed to measure the same steady passage of moments. Yet modern physics revealed something much more unusual. Time can slow down or speed up depending on gravity and motion. Near a black hole, this effect becomes extremely powerful. The idea sounds almost impossible at first because human beings experience time as stable during ordinary life. Seconds appear identical whether someone stands beside the ocean, walks through a city, or climbs a mountain. The passage from morning to evening feels reliable and predictable, yet beneath that familiar experience, time itself remains flexible. Gravity changes how quickly time passes. The stronger the gravity, the slower time moves compared to regions farther away. This strange relationship was predicted through the theory of general relativity developed by Albert Einstein in the early 20th century. Before Einstein, gravity was often imagined as an invisible force pulling objects toward one another through empty space. General relativity introduced a far deeper and stranger picture. According to Einstein, gravity is not simply a force acting across space. Gravity emerges because mass bends the framework of space and time themselves. Space and time are connected together into a single framework, often called space-time. Rather than existing separately, they function as parts of the same underlying framework of the universe. Massive objects like stars and planets distort this framework around them. Other objects then move along the curved paths created by that distortion. What people experience as gravity is actually motion through curved space-time. The sheet bends downward beneath the weight. If smaller marbles roll across the sheet nearby, their paths curve inward toward the heavier object. In a somewhat similar way, stars, planets, and black holes bend space-time around themselves. The greater the mass and density, the stronger the curvature becomes. Black holes represent the most extreme example of this process ever discovered. The amount of mass compressed into such a tiny region creates extraordinary curvature in space-time. Near the event horizon, the distortion becomes so severe that even light cannot follow a path outward. Space itself curves inward dramatically around the black hole. At the same time, time slows enormously compared to regions farther away. Imagine two clocks. One remains safely distant from a black hole, while the other approaches close to the event horizon. To an outside observer watching from far away, the clock near the black hole would appear to tick more slowly. Minutes near the black hole might correspond to much longer periods farther away. This effect is not an illusion or a problem with the clock itself. Time genuinely passes differently under stronger gravity. Scientists have confirmed smaller versions of this effect even near Earth. Atomic clocks placed at different altitudes measure tiny differences in time caused by Earth's gravity. Clocks farther from Earth's surface experience slightly weaker gravity and therefore run very slightly faster. The difference remains tiny under ordinary conditions, yet modern instruments can measure it accurately. Around black holes, however, the effect becomes enormous. This relationship between gravity and time creates situations that almost sound like science fiction. A person spending time near a black hole under certain conditions could experience far less time passing than people far away. While only hours or days pass nearby, years might pass elsewhere. Black holes therefore reveal that time is not absolute and universal. It changes depending on gravity and motion. Another surprising aspect of relativity is that space itself becomes distorted alongside time. Distances near powerful gravity no longer behave exactly the way people expect. Paths curve, light bends, motion changes. Around black holes, space-time becomes so warped that familiar ideas about direction and movement begin losing their ordinary meaning. Straight paths through space become curved trajectories shaped by gravity. To picture warped space-time more clearly, imagine driving across a flat plain where travel in any direction feels easy and predictable. Now imagine the landscape slowly changing into steep valleys and deep slopes. Movement becomes more difficult, and paths naturally curve along the shape of the terrain. Around black holes, space-time itself becomes shaped into something like a deep gravitational valley. Objects and light follow the curves created by that distortion. Einstein himself was initially uncertain whether black holes truly existed in nature. The mathematics of general relativity allowed such objects, yet they appeared so strange and extreme that many scientists doubted whether reality could actually produce them. Over time, however, observation after observation continued supporting the theory. The movement of stars, the bending of light, the slowing of time near gravity, and the existence of black holes themselves all match the predictions remarkably well. General relativity became one of the most successful scientific theories ever developed because it accurately describes gravity across enormous scales. It explains planetary orbits, the motion of galaxies, gravitational wave signals, and the behavior of black holes. Even technologies used daily on Earth, such as global positioning satellites, must account for relativistic time differences caused by gravity in order to function accurately. Black holes remain especially important because they push relativity into its most extreme territory. Near these objects, gravity becomes powerful enough to dramatically slow time and strongly bend space-time. Scientists study black holes partly because they provide opportunities to test physical theories under conditions impossible to recreate on Earth. They act as natural laboratories where the universe reveals its deeper rules. The relationship between gravity, space, and time also changes the way people think about reality itself. Space is not empty and passive. Time is not fixed and universal. Together they form a flexible framework, responding to mass and energy throughout the cosmos. Black holes reveal this hidden flexibility more clearly than almost anything else in the universe. When space and time become warped by gravity, objects no longer travel along the simple straight paths people naturally imagine. Instead, everything follows curves shaped by the framework of space-time itself. Planets orbit stars because they move through curved space-time created by stellar gravity. Moons circle planets for the same reason. Around black holes, this curvature becomes so extreme that motion itself begins behaving in ways far removed from ordinary human experience. On a perfectly level surface, the marble travels in a relatively straight line. Yet if the floor bends downward into a deep bowl shape, the marble curves inward while following the surface beneath it. Around massive objects, space-time behaves similarly. Matter and light move along the curves created by gravity. Black holes represent the deepest gravitational valleys known in the universe. Near Earth, these curves remain gentle enough that human beings barely notice them directly. Rockets still require enormous energy to escape Earth's gravity, yet everyday movement feels stable and predictable. Near black holes, however, the curvature becomes extremely intense. Space bends inward so strongly that familiar ideas about direction and escape begin breaking down. Paths that might appear outward from one perspective eventually curve back inward toward the black hole. This extreme curvature affects not only matter, but also light itself. Normally, light travels across space in straight lines at incredible speed. Yet near black holes, even light must follow the curved framework of space-time. Its path bends dramatically while passing close to the black hole. In some situations, light from distant stars loops partially around the black hole before continuing outward toward distant observers. The universe itself behaves almost like a giant lens shaped by gravity. Scientists call this effect gravitational lensing. Massive objects bend light, much like glass lenses bend light passing through them. Around black holes and galaxies, the effect can become powerful enough to distort the appearance of distant objects behind them. Astronomers sometimes observe stretched arcs, duplicate images, or glowing rings created entirely through curved space, time redirecting light across enormous distances. This balance between familiarity and strangeness makes black holes fascinating to scientists. The same physics governing a falling apple on Earth also governs stars orbiting supermassive black holes at galactic centers. The difference lies not in the existence of new magical forces, but in the scale and intensity of gravity involved. Black holes reveal what ordinary physics looks like when pushed toward its most extreme limits. Imagine standing beside a calm river flowing gently through a valley. Movement across the water feels manageable and predictable. Now imagine the river narrowing into steep rapids, rushing toward an enormous waterfall. The same water still follows the laws of fluid motion, yet conditions become much more intense and dangerous. Near black holes, gravity creates similar transitions. The familiar rules remain valid, but the environment becomes dramatically more extreme. One of the most powerful effects near black holes involves tidal gravity. Gravity does not pull equally on every part of an object when distances become tiny. The side closer to the black hole experiences stronger gravity than the side farther away. Around Earth, tidal forces from the Moon create ocean tides. Near black holes, tidal forces can become vastly more powerful. For a person or object approaching a smaller stellar black hole, these tidal differences could become severe enough to stretch matter dramatically. The process is sometimes described as spaghettification because gravity pulls more strongly on one end of the object than the other. Although the term sounds humorous, the physical effect itself reflects the immense difference gravity can create over short distances near black holes. Interestingly, supermassive black holes behave somewhat differently near their event horizons. Because their mass spreads across a much larger region, tidal forces at the event horizon may actually feel gentler compared to smaller black holes. An object crossing the horizon of a supermassive black hole might not immediately experience extreme stretching. Yet deeper inward, gravity would eventually become overwhelming. The extreme environments surrounding black holes also influence radiation, magnetic fields, and particle motion. Matter orbiting close to the event horizon moves at astonishing speeds while heating to extraordinary temperatures. Magnetic fields twist through the plasma surrounding active black holes. Radiation pours outward from spinning disks, while gravity shapes the motion of everything nearby. These regions become some of the most energetic places in existence. Despite these extraordinary conditions, black holes remain surprisingly orderly in many ways. Their behavior follows precise mathematical patterns described through relativity and physics. Astronomers can predict the orbits of stars around black holes. Scientists can calculate how light bends near gravity. Computer models simulate the motion of matter spiraling into spinning disks. Even one of the most extreme objects in the cosmos still obeys consistent physical principles. One especially fascinating discovery is that black holes often remain stable for immense periods of time. Once formed, they can persist across billions of years while quietly influencing surrounding matter through gravity. Entire galaxies evolve while their central black holes continue existing deep within the galactic core. The universe changes constantly around them, yet the black holes themselves remain anchored by the steady logic of gravity. Deep inside a black hole lies one of the greatest mysteries in all of physics. Beyond the event horizon, hidden from outside observation, theory predicts the existence of something called a singularity. This is the point where matter becomes compressed to extraordinary density under the force of gravity. The singularity represents a region where current scientific understanding begins to break down. Equations that describe stars, planets, motion, and even space-time itself can no longer fully explain what happens there. The idea of a singularity emerged naturally from the mathematics of general relativity. According to the equations, once enough matter collapses inward under gravity, the compression continues without limit. Density increases enormously, while space-time curvature becomes extreme beyond ordinary comprehension. In theory, the matter may collapse into a point of effectively infinite density where known physical laws can no longer operate normally. This concept feels deeply unsettling, because infinity rarely appears comfortably in physics. Science usually describes nature through measurable quantities and predictable relationships. Yet singularities represent places where those relationships stop functioning in familiar ways. It is similar to reaching the edge of a map, where the markings suddenly disappear into blank space. The equations continue pointing inward, but human understanding struggles to follow further. One reason singularities remain difficult to imagine is because nothing in ordinary life resembles them even remotely. Mountains, oceans, stars, and planets all possess framework and volume. Matter spreads across space. Even the densest materials on Earth still contain enormous empty regions between atoms. Inside black holes, however, gravity overwhelms every known force resisting compression. Matter collapses inward beyond anything human experience can easily picture. Imagine compressing the building into the size of a car, then into the size of a grain of sand, then smaller still. Gravity inside a black hole drives compression far beyond such examples, until ordinary ideas about size and framework lose meaning entirely. The density becomes extreme beyond normal intuition. Scientists do not believe the singularity necessarily means nature literally creates an infinitely small point in a simple, everyday sense. Instead, the singularity likely signals that current theories remain incomplete under such extreme conditions. General relativity describes gravity extremely well on large scales, yet it does not fully combine with quantum physics, which governs extremely small scales. Inside black holes, both gravity and quantum effects become important simultaneously. This conflict represents one of the biggest challenges in modern science. Physicists continue searching for a deeper theory capable of uniting gravity with quantum mechanics into a single framework. Black holes sit directly at the center of this problem because conditions near singularities push both theories to their limits. The universe therefore uses black holes almost like hidden laboratories, testing the boundaries of human knowledge. Some physicists have suggested that nature may hide singularities behind event horizons for a reason. This idea became known as cosmic censorship. According to the concept, the universe prevents singularities from becoming exposed directly to outside observation. If singularities were visible openly in space, the breakdown of predictable physics might create serious problems for understanding motion and causality. By remaining hidden, the singularity stays isolated within the black hole. For an outside observer, the event horizon therefore acts almost like a curtain separating known physics from unknown conditions deeper inside. Everything beyond the horizon remains inaccessible. No telescope can see through it. No signal escapes. No photograph can reveal the interior directly. The black hole preserves its deepest secrets behind gravity itself. Even light cannot escape from within the horizon to carry information outward. Normally, astronomers learn about distant objects through light arriving across space. Stars reveal their temperature and composition through radiation. Galaxies expose their framework through visible and invisible wavelengths. Black holes interrupt this process completely beyond the event horizon. No direct information from the interior can ever reach outside observers. This creates fascinating scientific questions about information itself. If matter falls into a black hole, what happens to the information describing that matter? Does it disappear completely? Is it somehow preserved? Can information truly be destroyed by nature? These questions became deeply important in theoretical physics because they connect black holes to the fundamental framework of reality. The famous physicist Stephen Hawking spent many years studying these problems. His work revealed that black holes may not be entirely black forever. Through quantum effects near the event horizon, Black holes can slowly release tiny amounts of radiation, now called Hawking radiation. Over unimaginable periods of time, this process could eventually cause black holes to lose energy and slowly evaporate. The discovery connected black holes directly to quantum theory in surprising ways. Yet even Hawking radiation does not fully solve the mystery of what happens deep inside the black hole. The singularity remains hidden beyond direct observation. Current theories continue struggling to describe the true nature of conditions there. Some researchers suspect space-time itself may behave differently under such extreme density. Others propose entirely new frameworks replacing the classical singularity predicted by relativity. Despite these unanswered questions, scientists still understand many aspects of black holes with remarkable accuracy. The motion of nearby stars, the bending of light, gravitational wave signals from mergers, and the behavior of spinning disks all match theoretical predictions closely. The mystery lies not in whether black holes exist, but in what ultimately happens at their deepest hidden center. One of the deepest questions surrounding black holes concerns information itself. When matter crosses the event horizon and disappears from outside view, what happens to the information describing that matter? In ordinary life, information about objects can usually still be recovered in some form. A burned book releases smoke and ash, yet the atoms still exist. A shattered glass changes shape, yet its matter remains present. Physics traditionally assumes information about physical systems is never truly destroyed. Black holes challenge that assumption in extraordinary ways. The event horizon forms a boundary beyond which no information can escape outward. Light cannot return. Signals cannot travel back across the horizon. From the perspective of distant observers, anything crossing that boundary effectively vanishes from the visible universe. This creates a serious puzzle because modern physics depends heavily on the idea that information remains preserved even when matter changes form. Imagine writing words onto a sheet of paper and placing it into a sealed box that can never again be opened. The information still exists inside the box, even if nobody can access it. A black hole appears far stranger because the information seems trapped permanently behind the horizon, while the black hole itself reveals very little about what fell inward. According to classical physics, a black hole can largely be described using only a few properties such as mass, spin, and electrical charge. This simplicity became deeply surprising to physicists. A black hole formed from collapsing stars, gas clouds, or countless different objects appears externally almost identical if the final mass and rotation remain the same. The detailed information about the original matter seems hidden beyond recovery. This became known as the black hole information problem, one of the most important unsolved questions in theoretical physics. The problem grows even stranger when quantum theory enters the picture. Quantum mechanics strongly suggests information cannot simply vanish from reality. Yet black holes appear capable of hiding or possibly destroying information behind the event horizon. Reconciling these ideas became one of the greatest scientific challenges of the modern era. Black holes therefore sit directly at the crossroads between gravity, quantum mechanics, and the deeper framework of reality itself. One reason black holes proved so scientifically valuable is because they combine many areas of physics into single environments. gravity becomes extremely powerful. Motion approaches the speed of light. Radiation behaves under intense curvature of space-time. Quantum effects may emerge near event horizons. Rather than studying these topics separately, black holes bring them together under extraordinary conditions. Mathematics became the primary language scientists used to explore these hidden environments. Since direct observation beyond the event horizon remains impossible, researchers rely heavily on equations to describe how black holes behave. Mathematical models predict how stars orbit near black holes, how light bends around them, how gravitational wave signals emerge during mergers, and how matter moves through spinning disks. This process reflects one of the remarkable strengths of science. Human beings can discover truths about invisible and distant objects through careful reasoning, observation, and mathematics. Long before black holes were directly observed indirectly through telescopes, equations predicted their existence. General relativity revealed that sufficiently compressed matter would create regions where escape became impossible. Decades later, observations confirmed many of those predictions with astonishing accuracy. The relationship between theory and observation became especially important in black hole research. Scientific theories alone are never enough. Predictions must eventually match evidence gathered from the universe itself. Over time, astronomers observed stars orbiting invisible masses, detected intense radiation from spinning disks, measured gravitational lensing, recorded gravitational wave signals from merging black holes, and even produced indirect images of black hole shadows. Observation repeatedly strengthened confidence in the theory. Researchers today continue studying black holes from many different directions. Astronomers observe stars and galaxies searching for new evidence. Physicists develop theories attempting to unite relativity with quantum mechanics. Computer scientists create simulations of spinning disks and gravitational interactions. Engineers build increasingly sensitive instruments capable of detecting faint signals arriving across billions of light years. Another active area of study focuses on Hawking radiation and the fate of black holes over immense periods of time. If black holes slowly lose energy through quantum effects, what ultimately remains after unimaginable ages pass? Could information somehow escape gradually through subtle quantum processes? These questions continue driving some of the most high-level theoretical work in modern physics. For many years, black holes were studied mostly through light, gravity, and the motion of nearby stars. Scientists observed glowing spinning disks, measured the bending of light, and tracked objects orbiting invisible masses. Yet another hidden feature of the universe remained waiting to be discovered. Space itself could move and ripple. Violent cosmic events could send waves traveling outward across space-time itself. Black holes would eventually help reveal this hidden motion through one of the greatest scientific discoveries of the modern era. When two black holes drift near one another, gravity slowly pulls them together into a long spiraling dance. Each black hole curves space-time around itself while orbiting the other at tremendous speed. As they circle closer and closer together, energy escapes outward through gravitational wave signals. The black holes gradually lose orbital energy, causing the distance between them to shrink over time. Eventually, they spiral inward so rapidly that a final collision becomes unavoidable. The merger of two black holes is one of the most powerful events known in the universe. Enormous amounts of energy release within moments as the black holes combine into a single larger object. Yet unlike exploding stars, these events often produce little visible light because black holes themselves remain dark. Instead, much of the energy travels outward as ripples moving through space-time itself. To picture gravitational wave signals more clearly, imagine dropping a stone into a calm pond. Waves spread outward across the water in expanding circles. Gravitational waves behave similarly, except the waves travel through the framework of space-time rather than through water. As massive objects accelerate and move under gravity, they create tiny distortions that spread outward across the universe at the speed of light. Einstein predicted the existence of gravitational wave signals through general relativity more than 100 years ago. According to his equations, accelerating massive objects should disturb space-time itself, producing ripples capable of traveling enormous distances. For decades, however, many scientists doubted whether such waves could ever be detected directly. By the time they reached Earth, the distortions would become unbelievably tiny. The difficulty of detection was almost unimaginable. A passing gravitational wave changes distance itself by a remarkably small amount. Objects become stretched and compressed by fractions far smaller than the width of an atom. Detecting such minute distortions required instruments of extraordinary precision and decades of technological development. The breakthrough finally arrived in the year 2015. Scientists working with the Laser Interferometer Gravitational Wave Observatory, commonly called LIGO, announced the first direct detection of gravitational wave signals. The signal came from two black holes merging more than 1 billion light-years away. After spiraling together for immense stretches of time, the black holes collided and released enormous energy into space-time itself. The ripples from that distant event traveled across the universe until finally reaching Earth. The discovery marked a historic moment in science. For the first time, humanity directly detected movement within space-time itself. The signal matched the predictions of general relativity with astonishing accuracy. Scientists could even reconstruct details about the black holes involved, including their masses and the final merger process, entirely from the gravitational wave pattern reaching the detectors. One remarkable aspect of gravitational wave astronomy is that it allows scientists to study the universe in an entirely new way. Traditional astronomy relies mostly on observing electromagnetic radiation such as visible light, radio wave signals, infrared radiation, and X-ray radiation. Gravitational waves provide a completely different source of information. Instead of seeing the universe through light, researchers can now listen to the motion of space-time itself. The observatories used to detect these waves are extraordinary instruments. The Laser Interferometer Gravitational Wave Observatory, commonly called LIGO, consists of enormous facilities with long vacuum tunnels arranged in giant L-shaped frameworks. Laser beams travel back and forth along these tunnels with incredible precision. When a gravitational wave passes through Earth, space-time stretches one direction slightly while compressing another. The laser measurements detect these tiny changes in distance. The precision required almost defies belief. The detectors measure distortions thousands of times smaller than the width of a proton. Vibrations from trucks, earthquakes, ocean waves, and even tiny environmental disturbances had to be carefully filtered out. Scientists spent decades refining the instruments before direct detection finally became possible. Soon after the first discovery, more gravitational wave events were detected from other black hole mergers. Each signal confirmed that black holes frequently collide and merge across the universe. Some mergers involved stellar black holes larger than astronomers previously expected. Others revealed new details about how black holes spin and orbit one another before collision. These observations transform black holes from largely theoretical objects into directly measurable cosmic systems. Scientists no longer relied only on indirect evidence from surrounding stars or radiation. Gravitational waves allowed researchers to observe black holes interacting through gravity itself. The universe opened an entirely new window for understanding extreme cosmic events. One especially fascinating detail is that black hole mergers briefly release astonishing amounts of energy. During the final moments before collision, the power emitted through gravitational wave signals can exceed the combined light output of all stars in the observable universe. Yet almost none of this energy appears as visible light. Instead, the energy travels silently outward through ripples in space-time itself. The merging process also demonstrates how dynamic the universe truly is. Space is not empty and motionless. Galaxies rotate, stars explode, black holes collide. Space-time itself moves and vibrates in response to enormous gravitational events unfolding across billions of light years. Much of this activity remained hidden from humanity until technology high-level enough to detect it. Gravitational wave astronomy remains a young field with enormous potential for future discoveries. Scientists hope to detect mergers involving neutron stars, supermassive black holes, and perhaps entirely new phenomena not yet fully understood. Future observatories may become sensitive enough to detect gravitational wave signals from the early universe itself, carrying information from cosmic epochs otherwise impossible to observe directly. When gravitational wave signals finally reached Earth in the year 2015, the signal lasted only a fraction of a second. Yet hidden inside that brief vibration was an enormous amount of information about the universe. Scientists could determine the masses of the black holes involved, how quickly they orbited one another, how far away the collision occurred, and even how much energy had been released during the merger. The universe had effectively transmitted a message across more than 1 billion light-years entirely through the motion of space-time itself. The signal detected by LIGO appeared as a tiny rising pattern, often described as a chirp. As the black holes spiraled closer together, they orbited faster and faster. The gravitational wave signals increased in frequency and intensity until the final collision occurred. Then the signal suddenly faded as the newly merged black hole settled into a stable form. That short pattern matched theoretical predictions with extraordinary precision. This agreement between theory and observation became one of the strongest confirmations of general relativity ever achieved. Einstein's equations had predicted gravitational wave signals more than 100 years earlier using mathematics alone. Long before humanity possessed the technology to measure space-time directly, the theory already described how black holes should merge and what signals they should produce. When the real observation finally arrived, nature followed the equations almost perfectly. For scientists, this moment carried enormous meaning because successful theories must survive comparison with reality. Mathematics alone cannot prove how the universe behaves. Predictions must eventually meet observation, Again and again, relativity continued passing these tests under increasingly extreme conditions. Time slowing near gravity, light bending around stars, gravitational wave signals from black hole mergers, and the motion of galaxies all match the deeper framework described through Einstein's work. The discovery of gravitational wave signals also expanded humanity's understanding of the universe in a profound new way. Before these detections, most astronomical knowledge came through observing forms of light. Telescopes collected visible light, radio wave signals, infrared radiation, ultraviolet radiation, and X-ray radiation arriving from distant objects. Gravitational waves added something entirely different. Scientists could now study invisible cosmic events directly through motion within space-time itself. This new ability changed astronomy similar to the invention of hearing in addition to sight. Imagine trying to understand Earth while only observing still photographs. Much information could still be learned, yet important details about storms, earthquakes, voices, oceans, and music would remain hidden. Gravitational waves revealed a hidden layer of cosmic activity previously impossible to sense directly. The universe contains many violent events that produce little or no visible light. Black hole mergers are one example. Since black holes trap light behind event horizons, collisions between them may remain almost completely dark to traditional telescopes. Yet the movement of the black holes disturbs space-time powerfully enough to produce detectable gravitational wave signals. Through these waves, scientists can observe events otherwise hidden entirely from ordinary view. Each new gravitational wave detection adds another piece to humanity's understanding of cosmic evolution. Some signals come from black holes larger than expected. Others reveal unusual orbital motion or different spin orientations. Over time, these observations help researchers understand how black holes form, grow, interact, and merge across billions of years across the universe. One especially fascinating aspect of gravitational wave signals is that they travel through space almost untouched by matter. Light can become blocked, scattered, or absorbed by gas clouds and dust. Gravitational waves pass through most material with almost no interference. This means they carry clean information directly from distant cosmic events. Waves produced by black hole mergers can cross enormous regions of the universe while preserving details about their origin. To imagine this more clearly, think about hearing thunder during a storm. Even if trees or buildings block the direct view of lightning, the sound still travels across the landscape, revealing that powerful activity occurred nearby. Gravitational waves behave similarly on cosmic scales. They carry information across the universe, even when no visible light reaches observers directly. Scientists now operate multiple gravitational wave observatories across different parts of Earth. Working together, these facilities help confirm detections and identify the approximate direction from which signals arrive. International cooperation became essential because the distortions being measured remain extremely tiny. Multiple detectors strengthen confidence that a real gravitational wave passed through Earth rather than a local environmental disturbance. Future observatories promise even greater discoveries. New instruments may detect lower frequency gravitational wave signals produced by supermassive black holes orbiting one another at galactic centers. Space-based detectors could eventually operate far from Earth, where environmental vibrations become weaker. These future systems may reveal gravitational signals from events currently beyond human detection. The study of gravitational wave signals also deepens understanding of space-time itself. Before relativity, space was often imagined as a passive, empty stage where physical events simply occurred. Modern physics revealed something much more dynamic. Space-time bends, stretches, compresses, and vibrates through gravity and energy. The universe possesses motion even at the level of its underlying framework. Black holes helped reveal this hidden motion because they produce some of the strongest gravitational effects known. When enormous masses accelerate rapidly during mergers, space-time responds dramatically. Waves spread outward, carrying energy through the cosmos itself. Entire regions of space gently stretch and compress as the ripples pass through them. The discovery of gravitational wave signals therefore connected humanity directly to events occurring across astonishing stretches of distance and time. Through delicate instruments and mathematical understanding, people learned to detect faint vibrations arriving from ancient cosmic collisions billions of light-years away. The universe revealed itself to be not only visible through light, but also alive with subtle movement woven into space-time itself. When many people imagine black holes, they picture enormous cosmic monsters constantly swallowing nearby stars and blasting powerful radiation across space. Popular films and illustrations often show violent glowing disks and dramatic streams of energy surrounding them. Yet the reality is often much quieter. Many black holes spend long periods doing very little at all. They drift silently through space without producing bright radiation or dramatic visible effects. In fact, the majority of black holes in the universe may remain almost completely hidden from observation. A black hole only becomes highly visible when enough matter exists nearby to feed it. Gas, dust, stars, or other material must move close enough for gravity to pull the matter inward. When this happens, spinning disks form and radiation escapes from the heated material surrounding the black hole. Without nearby matter, however, the black hole may remain dark and quiet for immense stretches of time. This idea surprises many people because black holes are often imagined as endlessly hungry objects pulling everything inward from vast distances. In reality, black holes obey the same gravitational rules as any other object with mass. If the Sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. The gravity far away would remain essentially the same. The difference becomes important only near the event horizon, where gravity grows extreme. A quiet black hole drifting through relatively empty space may produce almost no detectable radiation at all. No glowing disk forms. No bright jets emerge. No nearby stars become disturbed visibly. The black hole simply moves silently through darkness while remaining extremely difficult to detect directly. This means the universe may contain enormous numbers of hidden black holes still waiting to be discovered. Astronomers believe many stellar black holes likely formed throughout the history of galaxies as massive stars ended their lives and collapsed. Yet only a fraction of these black holes become obvious through active spinning disks or dramatic gravitational interactions. Most probably remain dormant for long periods while quietly orbiting within galaxies among ordinary stars. Some burn brightly because fresh wood feeds the flames continuously. Others glow faintly with only occasional sparks. Still others have almost no visible light remaining, even though hot coals still exist beneath the ashes. Black holes behave similarly. Their visible activity depends heavily on whether fresh material continues falling inward. This quiet behavior became important scientifically because it suggested that many black holes remain undetected across the cosmos. Astronomers cannot simply count glowing spinning disks to determine how many black holes exist. Many may never reveal themselves dramatically. Instead, scientists often search indirectly by studying the motion of nearby stars or observing subtle gravitational effects. Some hidden black holes may orbit companion stars without actively consuming large amounts of material. Others may drift alone through interstellar space after ancient stellar explosions. Supermassive black holes at galactic centers can also experience quiet periods lasting millions of years if little matter falls inward. Activity rises and falls depending on the surrounding environment. This changing activity reveals something important about black holes. They are not always violent cosmic engines operating at maximum intensity. Their appearance depends greatly on circumstances. Nearby gas clouds, passing stars, galactic collisions, and the surrounding environment all influence how active a black hole becomes over time. Scientists continue searching for hidden black holes, partly because understanding their true population helps explain galactic evolution and stellar history. If galaxies contain much more dormant black holes than currently observed directly, those hidden objects still contribute to the overall gravitational framework of galaxies. Their presence matters even when they remain invisible. Modern observatories increasingly detect black holes through indirect techniques rather than visible brightness alone. Tiny changes in stellar motion, subtle distortions of light, gravitational wave detections, and careful orbital measurements all help reveal otherwise hidden black holes. Astronomy, therefore, often depends on detecting influence rather than direct visibility. Even active black holes may eventually enter calmer phases when surrounding material becomes scarce. The bright spinning disks fade, jets weaken or disappear, radiation declines, yet the black hole itself remains, continuing to shape nearby motion through gravity while hidden in darkness. Activity changes, but gravity persists. Much of astronomy depends on studying objects that cannot be touched directly. Unlike mountains, oceans, or forests on Earth, distant stars and galaxies remain forever beyond physical reach. Scientists must therefore learn about the universe through observation, measurement, and careful interpretation of evidence. Black holes push this process even further because the objects themselves often remain invisible. Their existence is revealed mainly through the motion they create around them. One of the most important tools in astronomy is gravity. Gravity leaves traces everywhere it acts. Even when an object cannot be seen directly, its gravitational influence changes the movement of nearby matter. Stars shift position, gas clouds accelerate, light bends, orbital paths curve through space. By studying these effects carefully, astronomers can uncover hidden frameworks scattered across the universe. This process resembles daily experiences more than many people realize. Imagine entering a room where curtains move gently, although no fan is visible. The movement immediately suggests air flowing through the space, or imagine hearing footsteps behind a closed door. Even without direct sight, motion reveals the presence of something unseen nearby. Astronomy often works through the same principle. Hidden objects announce themselves through their influence on visible surroundings. Black holes became scientifically accepted largely because of these indirect observations. Long before telescopes produced detailed images of spinning disks or black hole shadows, astronomers noticed stars behaving strangely. Certain stars orbited invisible partners possessing enormous mass. Others moved through galactic centers at extraordinary speeds, impossible to explain through visible matter alone. Gravity exposed the hidden objects before direct evidence became available. One common example involves binary systems, where a visible star orbits an unseen companion. If the visible star moves in a repeating pattern without any detectable object nearby, scientists can calculate the mass required to create that motion. In some cases, the hidden companion proves too massive and compact to be an ordinary star, white dwarf, or neutron star. The evidence points instead toward a black hole. These calculations rely on the same physical principles governing motion across the universe. Planets orbit stars because gravity shapes their paths. Moons orbit planets through the same process. By measuring speed, distance, and orbital timing, astronomers can estimate the mass of unseen objects with remarkable accuracy. Motion becomes a kind of cosmic fingerprint, revealing hidden frameworks. One especially important discovery came through observing stars near the center of the Milky Way. Over many years, astronomers tracked their movement carefully, using high-level telescopes capable of measuring tiny positional changes. Some stars traveled along elongated orbits around an apparently empty point in space. Their speeds became remarkably high as they passed close to the hidden center. The motion could only be explained if an enormous amount of mass occupied a tiny region. No visible cluster of ordinary stars could remain stable under such conditions. The observations pointed strongly toward a supermassive black hole hidden at the galactic center. Again, the black hole itself remained unseen directly, yet gravity revealed its existence clearly through stellar motion. Indirect evidence also plays a major role in other areas of science. Human beings cannot see atoms with ordinary vision, yet experiments reveal their behavior through measurable effects. Magnetic fields remain invisible, yet moving compass needles expose their presence immediately. Wind, radio wave signals, and gravity itself cannot be seen directly, yet their influence becomes unmistakable through observation. Science often advances by interpreting the hidden causes behind visible effects. Black holes became one of the greatest examples of this principle. Even without direct visibility, their gravity organizes nearby motion in precise and measurable ways. Gas spirals inward through spinning disks. Stars orbit invisible centers. Light bends around massive regions of curved space-time. Gravitational waves ripple outward during mergers. Piece by piece, these observations build a detailed picture of objects hidden in darkness. One reason indirect observation remains so powerful is because the laws of physics behave consistently across the universe. Gravity affects motion predictably. Orbital mechanics follow mathematical relationships. Light responds to space-time curvature according to relativity. Because these rules remain reliable, scientists can infer hidden causes from visible outcomes with increasing confidence. Modern astronomy therefore resembles detective work on enormous cosmic scales. Researchers collect clues scattered across space and time. Tiny shifts in stellar movement, faint radiation patterns, subtle distortions of light, and gravitational wave signals all provide pieces of larger hidden stories. From those clues, scientists reconstruct events and objects impossible to observe directly. This method requires extraordinary patience because many astronomical processes unfold slowly over years or decades. Tracking stellar orbits near the Milky Way's central black hole required continuous observation across long periods of time. Detecting tiny gravitational effects demands precise instruments and repeated measurements. Science often advances gradually through persistent observation rather than sudden revelation. The first direct image associated with a black hole, released many years after indirect evidence had already convinced most scientists, did not suddenly prove black holes existed for the first time. Instead, it confirmed decades of earlier observations and theoretical predictions. Long before that image appeared, stars, gas clouds, and gravity had already revealed the hidden presence of black holes throughout the cosmos. One of the most common misunderstandings about black holes is the idea that they behave like enormous cosmic vacuum cleaners, pulling everything inward from vast distances. Films and illustrations often show stars, planets, and entire galaxies being swallowed uncontrollably the moment a black hole appears nearby. The reality is far calmer and more frameworked. Black holes obey the same gravitational rules as every other massive object in the universe. At large distances, their gravity behaves no differently than the gravity of stars or planets with equal mass. If the Sun were somehow replaced instantly by a black hole containing exactly the same mass, Earth would continue orbiting almost normally. The planet would not suddenly spiral inward and disappear. The orbit would remain largely unchanged because gravity at Earth's distance depends mainly on mass, not on whether that mass exists as a glowing star or a black hole. The major difference would simply be the loss of sunlight and heat. This fact surprises many people, because black holes are often imagined as possessing supernatural gravitational powers extending endlessly through space. In truth, gravity weakens with distance, according to familiar physical laws. The farther away an object is from a black hole, the weaker the gravitational pull becomes. At sufficiently large distances, a black hole behaves much like any other object of similar mass. The real danger exists near the event horizon, where gravity becomes extremely intense. Objects passing too close may become trapped, because escape would require speeds greater than the speed of light. Yet far away from the black hole, stable orbits remain entirely possible. Stars, gas clouds, and even entire solar systems can orbit black holes safely for enormous periods of time. This idea becomes easier to understand through ordinary examples from the solar system. Earth orbits the Sun because gravity holds it in a stable curved path through space. The Moon orbits Earth through the same process. Satellites orbit planets while maintaining predictable motion rather than crashing inward immediately. Gravity does not automatically pull every object directly into collision. Motion and distance work together to create stable orbital systems. Black holes participate in these same orbital relationships. Matter close to the event horizon experiences extraordinary gravitational effects, but farther away the behavior becomes more familiar. Some stars orbit supermassive black holes at galactic centers for millions of years without falling inward. Entire galaxies rotate around central black holes, while remaining structurally stable over immense stretches of time. Far upstream, the river may flow calmly enough for boats to travel safely. Closer to the edge, however, the current grows stronger and more dangerous. Beyond a certain point, escape becomes impossible because the water moves too rapidly toward the drop. Black holes behave similarly. At great distances, motion can remain stable and predictable. Near the event horizon, gravity overwhelms every possible escape route. This transition between stable regions and dangerous regions depends strongly on distance. The event horizon itself marks the true boundary where escape becomes impossible. Outside that region, objects may still escape if moving appropriately. Inside the horizon, every future path leads inward toward the black hole. The importance of distance and gravity appears across the universe. Earth's gravity feels strong nearby, yet astronauts aboard orbiting spacecraft experience relative weightlessness because they continuously fall around the planet rather than directly into it. The moon influences ocean tides strongly, yet people are not pulled visibly toward the moon while walking outdoors. Gravity changes dramatically depending on proximity. Black holes, therefore, do not wander through space randomly devouring entire galaxies. Galactic frameworks remain remarkably stable, despite containing supermassive black holes at their centers. Stars orbit according to gravitational balance and motion. Only matter traveling too close to the black hole faces serious danger of capture. Even matter approaching the black hole does not always fall directly inward immediately. Gas and dust often enter long spiraling orbits through spinning disks before eventually crossing the event horizon. Some material may even be redirected outward through jets or gravitational interactions. The environment around black holes remains dynamic and governed by physical laws rather than chaotic destruction. Scientists also study safe orbital regions around black holes through mathematics and computer simulations. Stable orbits can exist surprisingly close to the event horizon, depending on the black hole's mass and rotation. In theory, an observer orbiting a supermassive black hole at a safe distance might witness dramatic gravitational effects while still remaining outside the immediate danger zone. One reason the misconception about black holes became so widespread is because the phrase itself sounds frightening and absolute. The word hole suggests a kind of endless cosmic trap, swallowing everything nearby. In reality, black holes are physical objects with specific gravitational boundaries and predictable behavior. Their power becomes extreme close to the event horizon, not infinitely dangerous across all space. Understanding this helps place black holes into the broader context of cosmic framework. They are part of the natural architecture of galaxies, rather than unstoppable destroyers threatening the universe. Stars orbit them, matter interacts with them, galaxies evolve around them. Gravity creates both stability and danger, depending on distance and motion. This balance between order and danger appears throughout nature. Oceans remain calm in some regions, while storms create violent waves elsewhere. Volcanoes may remain dormant for centuries before erupting powerfully. Rivers flow gently upstream while becoming dangerous near waterfalls. Black holes similarly contain regions of stable motion alongside zones where gravity becomes overwhelming. Gravity becomes stronger as objects move closer together. This simple principle shapes everything from falling rain on Earth to the motion of galaxies across the universe. Near black holes, the same rule still applies, yet the increase in gravity becomes extremely dramatic. A small change in distance near the event horizon can produce enormous differences in gravitational force. This steep increase creates some of the most extreme environments known in nature. On Earth, people experience gravity as relatively stable because the planet is so large compared to human scale. Climbing a hill or standing atop a mountain changes gravity only slightly. The difference remains too small for ordinary senses to notice directly. Near black holes, however, gravity changes much more rapidly across shorter distances. Moving only a small amount closer to the event horizon can produce vastly stronger gravitational effects. This relationship between gravity and distance explains why the event horizon represents such an important boundary. Far away, stable orbits remain possible, and motion behaves in familiar ways. Closer inward, gravity strengthens dramatically. Beyond the event horizon, escape becomes impossible because space-time itself curves inward too severely. The closer matter approaches the black hole, the more powerful the gravitational effects become. At first, the incline feels manageable and easy to cross. Farther inward, movement becomes more difficult as the slope increases. Eventually, the terrain becomes so steep that climbing back out no longer remains possible. Around black holes, gravity creates a similar transition through curved space-time. Distance, therefore, matters enormously when studying black holes. A star orbiting safely far from the event horizon may experience relatively ordinary gravitational conditions. Matter spiraling inward through a spinning disk encounters increasingly intense gravity as it approaches the center. Near the event horizon, time slows dramatically, light bends severely, and tidal forces grow powerful enough to stretch matter itself. Tidal gravity becomes especially important because gravity does not pull equally on every part of an object when distances become small. The side nearest the black hole experiences stronger gravity than the side farther away. This difference creates stretching forces across the object. Near smaller black holes, the effect can become extremely intense over relatively short distances. Scientists sometimes describe this stretching effect using the informal term spaghettification, because objects become pulled into long, narrow shapes by uneven gravity. Although the name sounds unusual, the underlying physics follows ordinary gravitational principles. Gravity simply changes more rapidly with distance near black holes than under most conditions experienced elsewhere. Yet despite how strange these effects become, black holes still obey physical laws consistently. Their behavior remains predictable through mathematics and observation. Astronomers can calculate orbital motion around black holes with remarkable precision. Physicists can predict how light bends near intense gravity. Computer models simulate spinning disks, gravitational wave signals, and black hole mergers using known equations. This predictability is one of the most important features of black holes scientifically. Extreme does not mean chaotic. The environments surrounding black holes may become violent and energetic, yet the deeper rules governing those environments remain orderly. Gravity behaves according to relativity. Motion follows mathematical relationships. Radiation emerges through physical processes that scientists can study and model carefully. The same pattern appears in gravitational wave observations. Black hole mergers generate remarkably energetic events, yet the resulting wave patterns follow mathematical frameworks described by relativity. Scientists can compare observed signals to theoretical models and identify details about the merging black holes themselves. Order exists even within these enormous cosmic collisions. This balance between extremity and predictability gives black holes much of their scientific value. Because they obey consistent laws under extraordinary conditions, they become natural laboratories for testing physics. Researchers study black holes partly to understand whether current theories remain valid when gravity reaches immense intensity. At the same time, black holes also reveal where scientific understanding remains incomplete. Deep near the singularity, current theories begin breaking down. Physicists continue searching for deeper frameworks capable of uniting relativity and quantum mechanics. Yet even there, the expectation remains that nature still follows underlying order, whether humanity fully understands it yet or not. For decades, black holes remained objects understood mostly through mathematics, indirect observation, and scientific theory. Astronomers tracked stars orbiting invisible masses, detected radiation from spinning disks, and measured gravitational wave signals from black hole mergers. Yet despite all this evidence, no direct image connected to a black hole had ever been produced. The challenge seemed almost impossible. Black holes themselves emit no visible light, and their event horizons remain hidden within darkness. Still, scientists continued searching for a way to observe the region surrounding one of these mysterious objects more directly. The breakthrough finally arrived in the year 2019, when astronomers released the first image associated with a black hole. The image showed a glowing ring of light surrounding a dark central region. For many people around the world, the photograph became one of the most remarkable scientific images ever produced. After generations of theory and prediction, humanity had finally observed the shadow created by a black hole against the surrounding glowing material. The black hole in the image lies at the center of a distant galaxy called Messier 87, often shortened to Messier 87. This galaxy sits millions of light-years away from Earth and contains a supermassive black hole enormously larger than the one at the center of the Milky Way. The black hole itself contains billions of times the mass of the Sun and powers enormous jets extending outward across space. The dark center visible in the image is not the black hole itself in a simple, ordinary sense. Instead, the darkness represents the black hole's shadow against the bright surrounding material. Light from the glowing spinning disk bends around the black hole through intense gravity. Some light escapes toward Earth, while other light disappears beyond the event horizon. The result creates the striking appearance of a bright ring surrounding darkness. One reason the image became so scientifically important is because it matched theoretical predictions with remarkable accuracy. Long before the photograph existed, physicists using relativity had calculated how a black hole shadow should appear under such conditions. The size and shape of the observed ring closely matched those predictions. Once again, observation and mathematics aligned powerfully. Producing the image required one of the largest scientific collaborations ever attempted in astronomy. No single telescope on Earth possessed enough resolution to observe a black hole shadow directly from such enormous distance. Scientists therefore combined observatories across the planet into a coordinated network known as the Event Horizon Telescope. The Event Horizon Telescope does not function as one physical instrument located in a single place. Instead, it links radio telescopes spread across different continents, including observatories in North America, South America, Europe, Antarctica, and Hawaii. By synchronizing these facilities carefully, researchers effectively created a virtual Earth-sized telescope capable of extraordinary precision. This method relies on a technique called very long baseline interferometry. Each telescope records radio signals arriving from the black hole region with extremely accurate timing provided by atomic clocks. Later, vast amounts of data from all the observatories are combined using high-level computer processing. The synchronized observations allow scientists to reconstruct details far too small for individual telescopes to resolve alone. The amount of information collected during the project became enormous. Hard drives filled with observational data had to be physically transported between research centers because internet transfer alone would have taken too long. Teams of scientists and engineers worked together across many countries to process and analyze the signals carefully before the final image could emerge. Weather conditions also played an important role. Because the telescopes operated together across Earth, clear observing conditions were needed at multiple sites simultaneously. Researchers coordinated observations carefully to ensure the network functioned as a unified instrument. The achievement reflected not only high-level technology, but also extraordinary global cooperation. The final image itself appears relatively simple at first glance. A glowing uneven ring surrounds a dark center against black background space. Yet behind that image lies decades of theory, engineering, observation, and computation. The photograph represented the combined effort of hundreds of researchers working across nations and scientific disciplines. One especially beautiful aspect of the image is how it connects directly to the warped space-time surrounding the black hole. The bright ring forms, partly because gravity bends light dramatically near the event horizon. Some light circles around the black hole before escaping outward toward Earth. The image therefore captures not only glowing matter, but also the effects of curved space-time itself. The observation also reminded humanity that black holes are real physical objects, rather than abstract mathematical ideas alone. For generations, they existed mostly in equations and scientific discussions. Seeing the shadow produced by one of these hidden objects created a powerful emotional connection between theory and reality. The universe once again revealed something both strange and beautiful, waiting beyond ordinary human experience. Creating the first black hole image required much more than simply pointing telescopes toward the sky. The challenge involved gathering vast amounts of information from observatories spread across Earth and combining those signals into a single coherent picture. No individual telescope possessed enough resolving power to study a black hole shadow directly from such extreme distance. Scientists therefore developed methods allowing multiple observatories to work together as one enormous virtual instrument. Each telescope participating in the Event Horizon Telescope project recorded faint radio signals arriving from the region surrounding the black hole. These signals reached Earth after traveling across millions of light years through space. The telescopes captured tiny variations within the incoming radiation, while atomic clocks measured timing with extraordinary precision. Every observatory effectively collected one piece of a much larger puzzle. The process resembled listening to an enormous orchestra from many different locations at once. One microphone alone might capture only part of the music clearly, yet by carefully synchronizing recordings from many positions, the full performance could eventually be reconstructed with far greater detail. Around the world, telescopes gathered fragments of information that later became combined into a single image. The amount of data collected during these observations became remarkably large. Modern black hole imaging projects produce much more information than ordinary computers can process easily in real time. Researchers filled massive storage systems with observational data gathered from each telescope site. Some observatories existed in extremely remote locations, including high mountains and Antarctica, making transportation and coordination especially difficult. Because the files became so enormous, much of the data had to be physically transported using hard drives rather than transferred electronically across the internet. Teams carefully carried the information between research centers where powerful computer systems later synchronized and analyzed the observations. Months of processing followed before scientists could reconstruct the final image successfully. The imaging itself also relied heavily on indirect methods. Black holes remain fundamentally dark because light cannot escape from within the event horizon. The famous image from year 2019, therefore, did not show the black hole directly in the ordinary sense. Instead, astronomers observed radiation from the surrounding spinning disk and reconstructed the shadow created by the black hole's gravity against that glowing background. This indirect approach reflects a broader pattern throughout astronomy. Much of the universe becomes understood not through direct viewing alone, but through interpretation of surrounding evidence. Scientists study invisible exoplanets through the tiny dimming of stars. Dark matter reveals itself through gravitational effects. Black holes become visible through warped light, orbital motion, spinning disks, and gravitational wave signals. Observation often depends on reading hidden patterns within visible signals. Technology made these discoveries possible because the universe frequently operates on scales far beyond ordinary human senses. Black hole shadows appear remarkably small from Earth, despite the enormous size of the objects involved. Observing them required instruments capable of detecting tiny details across cosmic distances. Advances in radio astronomy, computing power, timing systems, and data analysis all contributed to the success of the project. One remarkable aspect of modern astronomy is how many scientific fields now work together during major discoveries. Engineers design precision instruments. Computer scientists develop algorithms for processing data. Physicists build theoretical models. Astronomers coordinate observations and interpret results. Large projects often require global collaboration between hundreds of specialists working toward shared goals. The relationship between theory and observation also became especially important during black hole imaging. Long before the Event Horizon Telescope existed, physicists already predicted roughly how a black hole shadow should appear based on relativity. Computer simulations modeled how light bends near event horizons and how glowing spinning disks might behave under extreme gravity. When the actual observations arrived, scientists compared the data carefully with theoretical expectations. The observed image closely matched the predicted frameworks, strengthening confidence in both the observations and the underlying physics. This process represents one of the great strengths of science. Theory guides observation, while observation tests theory. Each helps refine and strengthen the other over time. Black holes therefore became not only astronomical objects, but also testing grounds for human understanding itself. Every successful prediction confirmed that mathematics could describe reality across astonishing scales and conditions. Gravity-bending light near black holes followed the same deep principles predicted decades earlier through abstract equations. The universe once again behaved according to hidden order, waiting to be uncovered through careful study. Technology continues expanding humanity's ability to observe regions once thought inaccessible forever. Earlier generations could not imagine measuring gravitational wave signals or imaging black hole shadows. Future observatories may eventually reveal even sharper details surrounding event horizons or detect entirely new phenomena still hidden from current instruments. Scientific understanding grows alongside technological capability. One especially fascinating possibility involves studying black holes dynamically, rather than through single images alone. Researchers hope future observations may capture changing frameworks within spinning disks, or track matter moving near event horizons in real time. Improved sensitivity and coordination could reveal motion around black holes with increasing clarity. The advancement of astronomy also changes humanity's emotional relationship with the universe. Ancient civilizations saw black night skies filled with mysterious lights beyond understanding. Modern science transformed many of those mysteries into measurable physical systems, while simultaneously uncovering even deeper layers of wonder. Black holes, once considered impossible mathematical curiosities, became observable frameworks linked directly to gravity, space-time, and cosmic evolution. Observation and theory therefore continue working together like two halves of the same process. Theory proposes hidden frameworks and predicts behavior. Observation tests those ideas against reality. New discoveries then inspire deeper theories and improve technology. Step by step, humanity expands its understanding of the cosmos through this continuing dialogue between mathematics and evidence. Black holes are much more than isolated objects drifting silently through space. Over time, scientists realized that black holes connect together many of the deepest ideas in physics. Gravity, energy, motion, radiation, space-time, thermodynamics, and quantum theory all meet within the environment surrounding black holes. Few other objects in the universe combine so many different areas of science into a single system. Because of this, black holes became some of the most important natural laboratories for understanding reality itself. Gravity forms the foundation of every black hole. Without gravity, stars would never collapse inward, far enough to create event horizons or singularities. Yet black holes also reveal gravity behaving under its most extreme conditions. Space bends dramatically, time slows, light curves through warped space-time, matter accelerates toward incredible speeds. Black holes therefore push gravitational physics far beyond the gentle conditions experienced on Earth. At the same time, energy plays an equally important role. Matter spiraling into black holes releases vast amounts of heat and radiation. Accretion disks glow brighter than galaxies. Particle jets stretch across intergalactic distances. Gravitational waves carry energy outward during mergers. Black holes transform gravity into visible and measurable energy across the cosmos. Space-time itself also becomes deeply important near black holes. Earlier generations often imagined space as emptiness, and time as something separate, flowing steadily everywhere. Relativity revealed a much stranger picture, where space and time connect together into a flexible framework shaped by mass and energy. Black holes demonstrate this framework dramatically. Their gravity bends space-time so severely that ordinary intuition begins failing near the event horizon. One reason black holes fascinate physicists so strongly is because they expose tensions between different scientific theories. General relativity describes gravity extremely well on large scales. Quantum mechanics describes extremely small particles and microscopic behavior with astonishing precision. Yet near black hole singularities, both theories become important simultaneously. Current physics still struggles to combine them fully into a single unified framework. This challenge turned black holes into testing grounds for theoretical physics. Scientists use them to explore whether deeper laws may exist beneath current understanding. New ideas about quantum gravity, space-time framework, information, and cosmic evolution are often examined through black hole research because these objects push existing theories toward their limits. Under ordinary conditions, the bridge may appear completely stable and safe, yet engineers learn much more by placing the framework under heavy stress to reveal its deeper strengths and weaknesses. Black holes perform a similar role for physics. They expose theories to extreme conditions where hidden limitations or deeper patterns may emerge. Over the past century, black holes repeatedly confirmed major scientific ideas through observation. The bending of light near gravity matched relativity. Time dilation measurements agreed with theoretical predictions. Gravitational waves from mergers followed patterns described mathematically decades earlier. The first black hole image resembled computer simulations produced before the observations occurred. Again and again, nature validated the deeper framework predicted through theory. Yet black holes also continue revealing unanswered questions. What truly happens at singularities? How does information behave beyond event horizons? Can space-time itself possess a deeper microscopic framework? Did black holes influence the formation of early galaxies? Could entirely new physics emerge under such extreme conditions? These mysteries continue driving scientific research forward. Black holes also help scientists understand the universe on larger scales. Modern astronomy increasingly shows that galaxies and supermassive black holes evolved together over billions of years. The activity surrounding black holes influences gas clouds, star formation, and galactic framework. Rather than existing separately from cosmic evolution, black holes participate directly in shaping the universe itself. The early universe likely looked very different from the calm night sky visible above Earth today. Young galaxies collided frequently. Gas clouds moved through dense cosmic environments. Star formation occurred rapidly across enormous regions. Somewhere within that ancient chaos, early black holes formed and began growing. Their gravity and energy may have influenced the framework of galaxies from the beginning of cosmic history. Some supermassive black holes appear surprisingly large even in the young universe. Astronomers continue investigating how these enormous objects formed so quickly after the first galaxies appeared. The answers may reveal important clues about cosmic evolution, dark matter, and the behavior of matter under extreme conditions during the universe's earliest eras. Black holes therefore connect not only to local physics, but also to the broader story of cosmic history. They participate in the life cycles of stars, the framework of galaxies, and the movement of matter across immense spans of time. From stellar collapse to galactic evolution, gravity shapes the universe through processes linked directly to black holes. The study of black holes also changed humanity's philosophical understanding of reality. Earlier scientific eras often imagined the universe as mostly simple, stable, and mechanical. Modern physics revealed a cosmos where time stretches, space bends, invisible waves move through space-time, and hidden objects influence galaxies from deep within darkness. Black holes became symbols of how much deeper and stranger reality truly is beneath ordinary human experience. At the same time, black holes demonstrated the extraordinary power of human curiosity and reasoning. Through mathematics, observation, and technology, humanity learned to study objects millions or billions of light-years away that cannot even be seen directly. Scientists reconstructed hidden cosmic events, from faint signals arriving across space-time itself. The universe became understandable not because it was simple, but because physical laws remained discoverable through patient investigation. Black holes continue inspiring new generations of research because they stand at the edge between known and unknown physics. Every improvement in telescopes, gravitational wave detectors, computer simulations, and theoretical models reveals deeper layers of complexity waiting to be explored. The more humanity learns about black holes, the more they illuminate the framework of the cosmos itself. Across the observable universe, black holes exist in enormous numbers. Some formed from ancient stars collapsing billions of years ago. Others grew slowly at the centers of galaxies, while gathering matter across immense stretches of time. From small stellar remnants drifting quietly through space to supermassive giants hidden inside galactic cores, black holes became woven into the large-scale framework of the cosmos itself. Modern astronomy increasingly shows that galaxies and black holes are deeply linked together. Nearly every large galaxy studied carefully appears to contain a supermassive black hole at its center. The size of the black hole often relates closely to the size and framework of the surrounding galaxy. This connection suggests they evolved together rather than separately. Galaxies helped feed growing black holes, while black holes influenced the galaxies surrounding them through gravity and energy. This relationship may have shaped cosmic history across billions of years. During the early universe, galaxies collided frequently, while enormous gas clouds drifted through dense regions of space. Supermassive black holes likely grew rapidly during this era by consuming matter and merging with one another. Their activity may have influenced how stars formed inside young galaxies and how matter spread through cosmic frameworks. Today, astronomers continue mapping black holes across the universe using many different techniques. Some reveal themselves through glowing spinning disks. Others become visible through gravitational wave signals produced during mergers. Some expose their presence through the rapid motion of nearby stars. Many likely remain hidden entirely, except for their quiet gravitational influence on surrounding matter. The universe therefore contains much more black holes than humanity can currently observe directly. Countless hidden objects drift silently through galaxies without producing visible radiation. Entire populations may remain undetected because they lack nearby material to illuminate them. Yet even unseen, their gravity still contributes to the architecture of the cosmos. One especially fascinating realization is that black holes helped shape frameworks far larger than themselves. A supermassive black hole may occupy a region smaller than the solar system, while influencing stars across enormous galactic distances. Through gravity, radiation, and particle jets, black holes affect gas clouds, stellar motion, and the evolution of surrounding matter over immense spans of time. Gravity itself emerges as one of the central themes connecting everything learned about black holes. Gravity forms stars, shapes galaxies, bends light, slows time, and creates event horizons. Under ordinary conditions, gravity may seem gentle and familiar, yet black holes reveal how powerful and strange gravity can become when matter compresses into extreme density. The study of black holes also transformed humanity's understanding of matter itself. Matter is not infinitely stable or permanent in the ways earlier generations once imagined. Stars can collapse. Energy and mass connect deeply together. Space and time respond dynamically to gravity. Black holes revealed that the universe operates through relationships much more flexible and interconnected than everyday experience suggests. At the same time, black holes demonstrated the extraordinary reach of scientific discovery. Human beings evolved on a small rocky planet, orbiting an ordinary star within one galaxy among billions. Yet through observation, mathematics, and technology, humanity learned to detect invisible objects millions of light-years away and study how they bend space-time itself. Black holes became symbols of both cosmic mystery and human curiosity. Even now, observatories across Earth continue searching for new black hole signals arriving from deep space. Telescopes monitor galactic centers, while gravitational wave detectors listen for ancient mergers rippling through space-time. Computer simulations grow more high-level each year. New theories continue exploring what may happen near singularities and event horizons. Scientific understanding keeps expanding slowly outward into the darkness. The universe itself also continues evolving around these hidden objects. Stars are still collapsing into black holes tonight somewhere across distant galaxies. Supermassive black holes continue feeding quietly at galactic centers. Ancient gravitational wave signals still cross the cosmos, carrying records of collisions that happened long before human civilization existed. Black holes remain active participants in the ongoing story of cosmic evolution. For all their mystery and power, black holes are not separate from the universe. They are part of the same natural order shaping stars, planets, galaxies, and space-time itself. The same physical laws governing falling rain on Earth also govern matter spiraling toward event horizons billions of light-years away. Black holes reveal the universe operating at its most extreme, while still following deep mathematical framework. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about the hidden world of black holes.